Ravishka Rathnasuriya. Today I'll be speaking about our paper SoK Efficiency Robustness of Dynamic Deep Learning Systems. This work is collaborated with Tingxi, Zexin, Sohe Song, Mirazul, Haque, Simin, Chen, and Dr. Wei Yang, and we are from the University of Texas at Dallas. In real world, efficiency is really important. Efficiency is tightly tied to deployment in computation resources. Efficiency enables models to operate in real-time applications. Efficiency is crucial for edge devices, and efficiency is also tied to sustainability. The key idea behind dynamic deep learning system is that they can adapt their computations to the complexity of the input. Instead of treating every input the same, they adjust how much efforts they spend. This adaptive behavior is what makes dynamic deep learning systems powerful. They promise efficiency gains, which is highly attractive for real-world deployment. While this adaptivity makes dynamic deep learning system efficient, it also opens doors to the new risk because system adjust computations based on the input. An adversary can craft inputs that intentionally trigger higher computation efforts. This kind of vulnerabilities is particularly dangerous in real-time and resource-constrained environment because it can lead to delays, slowdowns, or even denial of service attacks. Let's formalize efficiency attacks. Unlike traditional accuracy-based attacks, efficiency attacks, the goal of the adversary is to inflate the computational cost. We can formulate this as an constraint optimization problem. Given a dynamic deep learning system N takes an input X and hardware accelerator H, the computational cost can be measured in terms of energy consumption, latency, or floating point operations. The goal of the adversary is to seek the perturbation delta that is imperceptible and within the valid input space while maximizing the computational cost. To better understand efficiency vulnerabilities, we first introduce the concept of dynamic behaviors in dynamic deep learning system. As shown here, the dynamic deep learning system adapt their computations to inputs such as images, speech, or text that are processed. This adaptability spans in three dimensions: D1 variant computations per inference, D2 variant number of inference iterations per input, D3 variant number of outputs sent to the downstream modules. In terms of D1, here the idea is that the system can adjust internal execution paths during a single forward pass. For example, certain layers, neurons, or solver steps may be skipped or activated depending on the confidence score or gating logic. For D2, unlike D1, which adapts within the single forward pass, D2 is about models that generate or refine outputs across multiple iterations, where the number of iterations is decided at runtime. This is very common in autoregressive and iterative generation models. For example, language models, the tokens are generated step by step until a stop token appears. For D3, here the number of outputs a model produces and inference can vary. This is typical in applications like object detection and multi-object tracking. Importantly, this adaptability is governed by internal decisions such as non-maximum suppression thresholds rather than fixed input sizes. Let's first talk about the attacker's goals. The goal of attacker is to maximize the computation cost, keep perturbations imperceptible to the users, and ensure adversarial inputs remain realistic and valid in deployment. The adversary has the knowledge and capabilities. First, in terms of adversarial knowledges, the adversary can use evasion attacks such as white box and black box, and also leverage poisoning attacks which happen during training, but the effect is felt during inference. Towards this, the adversary has the capability of doing data poisoning and model poisoning. Next, let's go over our taxonomy. Our taxonomy is mainly derived from the three dynamic behaviors we mentioned earlier. Based on these dynamic behaviors, we studied the dynamic mechanisms, and for each dynamic mechanism, we studied the system models under attack. For each system models, we studied attack strategies and their attacks. For more detailed overview of our taxonomy and more detailed overview of each attack strategies can be found in our paper. Next, let's start briefly talking about attacks in D1 skipping mechanism. Uh, Skipping is used in many systems such as multi-exit DNNs, dynamic width networks, multi-exit language models, and multi-exit vision transformers. These models use mechanisms like early termination or skipping blocks to save computations on easy inputs. But with attacks, the adversary introduces perturbations that suppress the skipping conditions. Instead of taking shortcuts, the model is forced to process all residual blocks or gates every time, even on easy inputs. We found 5 whitebox attack strategies. Gradient manipulation attacks, where attackers use inputs using internal gradients to bypass early exits. Multi-objective optimization, where perturbations balance the cost, plausibility, and stealth while increasing the computation without conflicting gradient signals that would weaken the attack. Next, the gradient approximation based attacks, where when the gradients are hard to get, attackers approximate them through entropy maximization to lower the intermediate classifier confidence. And also, attackers can use generative adversarial networks, where generators craft natural looking inputs that trigger heavy computations. Lastly, gradient manipulation, where importance token targets the key token and perturb or replace this key token to suppress the early exits. In terms of black box attacks, without gradients, the attackers use a learned estimator or genetic search to evolve the costly inputs. And also, during poisoning attacks, training data is poisoned to bias the model into inefficient execution paths. In the real world, such as devices like Galaxy S9 Plus, these attacks can drop the number of successful inferences from about 10,000 to just over 3,500. In IoT deployment, where resources are already limited, skipping attacks can cause delays up to 5 times, which is devastating for latency sensitive applications. These implications results that new attacks should focus on joint optimization between gate activation and inputs, and these attacks should be extended to newer architectures such as mixture of experts and mixture of depths. And also portability, such as developing hardware agnostic black box attacks should be focused. Next, let's move on to the step size based attacks. Here, the main attack system under attack is the ODE nets. Ordinary differential equation networks 3 forward passes as solving a differential equation with a numerical solver that adaptively picks the step sizes. Small steps improve accuracy but cost more compute. Large steps are faster but risk infidelity. This attacks perturbs input to solve so that the solver is forced to take smaller step sizes more often. By propagating through the solver, these attacks craft perturbations that inflate the number of integration steps and slow the model. These attacks transferabilities can be tried on both cross solvers and cross architectures. In the real world impact, these attacks can be vulnerable in DNN based compiler vulnerabilities, where step size manipulation can cut inference efficiency by up to 50%. In terms of implications, there should be balance between step size and energy efficiency in ODE solvers, as well as there should be growing research opportunities for black box based attacks on ODE solvers, because ODE solvers in the real world is currently growing. Next, let's move on to the Spiking attacks. The main system model is spiking neural networks, which are designed for mimicking the biological neurons. They process information through discrete spike. This event-driven design makes them attractive for low-power applications. The attacks uses surrogate gradients to bypass the non-differentiability of the spikes and optimize such the input to maximize the spiking activity while still keeping the outputs correct. Variance includes full backpropagation through time or reduced time steps through proxy models. Currently, there's no black box or poisoning attacks being evaluated. In the real world, these spiking attacks can be impact in power budget collapse in new neuromorphic or low power systems like camera and wearables, and also memory overload can fall back to cloud inference in edge devices. In terms of implications, these spiking neural networks should be extended to the non-image data such as text, video, or temporal signal data, and also developing black box efficiency attacks for spiking neural networks is an open problem. Next, let's move on to the sparsity based attacks. Dynamic sparsity is a key optimizations that accelerators such as ASIC or contrast vision transformers rely on. By skipping zero or near zero activations, these systems save both time and energy, but adversaries can exploit this by intentionally breaking the sparsity pattern, focusing on hardware to run denser or more expensive computations. White box attacks focus on layer-wise sparsity, then manipulates gradients to shift activations away from zero or making sparse layers dense. Gradient approximations inject synthetic outlier disrupting contrastation so that models switch from low precision to high precision computation. In the black box sparsity attacks, even without the full model access, the attackers can analyze the input-output patterns and use surrogate gradient estimation to reduce sparsity. Poisoning attacks modifies the sparsity in these parameters, increasing the non-zero activation with very little data poisoning. In the real world, the sparsity attacks can be affected in safety-critical IoT or machine learning as a service-based systems. And also batch sensitivity in sparsity is critical, where smaller batch sizes can increase memory up to 12%, and while the larger batch sizes can increase only up to 1.8%. However, implications relate cost-effective strategies beyond sparse gradient reliance. There should be balance between accuracy and efficiency in black box attacks. Study on impact on large-scale models with billions of parameters another open opportunities. While moving from D1, let's move on to the D2. The dynamic inference iterations capture how models like autoregressive decoder decides on the fly how many steps to run before halting. Normally, decoder stops when it predicted the end of sequence or EOS token. Like in this slide, the adversarial perturbation can suppress the likelihood of EOS token. Here, let's study the system under models. Dynamic inference iterations are especially relevant to autoregressive models. Towards this, there are four system models under attack, such as neural image caption generation, neural machine translation system, and speech system, and vision language models. Towards this, we study few of the attack strategies. First is the gradient guided sequence control, where the attacker propagates through the decoder to push down the EOS probability so the generation keeps going. Next is token replacement and removal. Use gradients to replace or remove the token signal stopping, removing shortcut queues that end early generation, and also leveraging genetic or evolutionary algorithm strategies, where evolve candidate inputs via mutated and crossover with a fitness function instead of using gradients. And also, in terms of black box attacks, Attackers can train or reuse a surrogate model to transfer and discover examples. Transferability makes these attacks practical against closed systems. Next, in terms of real-world impact, here on mobile devices, efficiency attacks can drain resources very quickly. For example, a neural machine translation attack can drain nearly about 30% of battery in 300 runs compared to 1% of battery drainage with using the benign input. On cloud devices, sponge examples on ASA translation can cause up to 6,000 times slowdown. In terms of implications, currently these models are use only fixed number of inputs or tokens. However, extending these models to larger token lengths is an open problem. Also, black box attack strategies should be investigated so that closed source models like GPT can be attacked. And also, efficiency optimization gradient based white box attacks can be used to cut the overhead. Let's move on to the D3 attack. These attacks focus mainly on object detection or tracking pipeline detectors normally emit a small set of boxes which are filtered by non-maximum suppression and then handled to the trackers. Under attack, adversarial input can cause detector to generate a large number of redundant phantom boxes or vastly increasing download workload. Towards this, we found few white box attack strategies: point cloud manipulation, where perturbs in LiDAR-based systems to create phantom object; bounding box manipulation, where the input force detectors to emit redundant and overlapping boxes, multiplying NMS and association cost; spatial attention, where adversarial noise redirects into attention to irrelevant regions; feature manipulation, perturbation densify the activations, defeating the sparsity or quantization so hardware runs on costly full precision computation. In terms of transferability, ensemble-based or universal perturbation increase the cross-model risk. Poisoning and backdoor attacks can implant high triggers during training so that specific input later causes bounding box explosions. In terms of real world, UAP attacks on video increases inference time by 251%, and also the frame rate drops from 40 fps to 16 fps. In terms of implication, there should be growing research area for black box attacks for real world system with unmodeled access. Also, hybrid strategies can be leveraged to with the adaptive methods. Next, we also investigated the resiliency of existing defenses within these attacks. For this, we studied two types of defenses. First is detection, where typically relies on input validation. For example, by training a support vector machine classifier to flag suspicious inputs, the classifier learns from the intermediate states or hidden features that can block the adversarial samples before they trigger the expensive computation. Next is the mitigation. Here the idea is to weaken the effect of adversarial perturbation rather than block them outright. A simple practical example is applying transformations such as JPEG compression and spatial smoothing, which reduces the high frequency noise that attack rely on. In our work, we tested both these strategies: detection through SVM-based input validation and mitigation using JPEG compression and spatial smoothing. We evaluated three attacks, namely NICG slowdown, deep sleuth, and slow track. Next, let's talk about the experimental results for mitigation effectiveness of NICG slowdown-based attacks. The key idea here is that without any defenses, the adversarial drastically increase the computation cost and output length explodes from 10 tokens to 62 tokens. However, JPEG compression reduces the tokens to 11 tokens. However, the blue score is very low. And the key takeaway within this experiment is that the main conclusion is that JPEG partially restored the efficiency but significantly hurt the fidelity, while smoothing largely ineffective against adversarial efficiency attacks. In terms of mitigation effectiveness for multi-exit networks, our key takeaway here is that overall JPEG and smoothing provide partial recovery, but multi-exit networks remain highly vulnerable under infinity attacks. The coefficiency benefit of these models cannot be reliably preserved under adversarial conditions. In terms of experimentation results from the detection base, our key takeaway is detectors work reasonably well on clean and adversarial inputs in isolation. However, once JPEG or smoothing are applied, detection essentially fails. The model becomes overconfident but loses separability between the benign and adversarial inputs. Our key takeaways are below. We studied the real-world threat, and we also address limitations of the attacks, and we also provide future research directions. More information can be found in our paper. And also, we have provided the link for our artifact and experimentation source code. Thank you.